Dear attendants of the Picture Coding Symposium 2021. My name is Michael Schaefer, and I'm very honored to give this video presentation about the research that my colleagues and I have done at the Fraunhofer Heinrich Hertz Institute in Berlin. Over the past 20 years, our Video Communication and Applications Department has made hundreds of contributions to the standardization of video coding technologies, also publishing at numerous IEEE conferences and journals. The present talk will concern the matrix-based intra-prediction tool, which was adopted into the VVC standard as a Luma-only method. This was due to certain design features, which impaired an application to the chroma component. However, our research group found that in certain cases, this restriction is no longer necessary. In fact, the application of MIP to the chroma component proves to significantly improve the coding gain. The presentation is structured as follows. The first part will provide some information on the VVC standardization process and how it affected the development of the MIP tool. Then we will briefly describe the tool itself and explain how we extended it to 444 chroma formats. Although the extension is fairly simple, its impact on the coding gain for natural content sequences turns out quite significant. So let's get started. Every year, Sandvin Incorporated issues a global internet phenomena report, which certainly backs up the need for novel video coding technologies. Video signals account for 60% and more of the current internet traffic, with growing supply of high-resolution content. Therefore, in 2013, HEVC was finished as the successor of the still widespread AVC standard, which provided substantial bitrate savings. Compared to the 10-year gap between these standards, the first exploration activities for a new codec started shortly after HEVC's release. In 2017, more than enough evidence was collected for initiating a new standardization process, and therefore, 1 year later, the development of the versatile video coding standard began. Again, the goal was to cut the average bitrate in half compared to the previous standard. As HEVC, VVC uses a hybrid block-based architecture with intra-picture prediction, motion-compensated prediction, transform coding, and an entropy coding stage. As a novel approach, our research group at HHI has investigated whether entirely new intra-prediction modes can be derived from a training experiment, given a suitable and large video database. Note that the conventional angular and planar prediction modes from HEVC can be written as linear functions. When we allow the prediction to be any function f, say a neural network with weights theta, to be optimized, we may substantially improve the prediction accuracy. Here, I will not give much detail on the training algorithm, since it is out of the scope of this presentation. Let me just remark that the use training objective should incorporate as many aspects of a hybrid video codec as possible. For instance, we developed a loss function which reflects properties of the residual quantization and trained on different block sizes and block partitions. This brings us to the main question, which function f to pick. In the initial CFP response from HHI, our research group has proposed a tool called intra-picture prediction with neural networks. Our network has multiple prediction modes which were co-adapted simultaneously during the training stage. We then simplified the resulting predictors by pruning them in the frequency domain of the discrete cosine transfer, thus greatly reducing the number of weights otherwise needed for the dense matrix vector multiplications. We demonstrate BD rate savings up to 6.2% over the VVC test model 1.0, using 16-bit integer weights, which accumulate to 11 megabytes of total memory. Also, the decoder runtime overhead seems modest compared to other neural network-based techniques for video coding. However, during the VVC standardization, several experts from different hardware manufacturers established narrow limits for the implementation of data-trained intra-prediction modes. In particular, the total capacity of the weights should not exceed 8 kilobytes of memory, and desirably, Each weight should be stored as an 8-bit value at sufficient precision. Another constraint is the number of multiplications. The new intra-prediction modes should not be more complex than existing intra-modes, which require far multiplications per sample to predict. Hence, we gave up on our initial network architecture and instead trained multiple linear prediction modes, still using our self-developed loss function and training algorithm. This led to the development of the matrix-based intra-prediction tool, which was finally adopted into the standard after some minor design modifications. So, let me introduce to you the MIP modes. These modes exist next to the conventional intra-prediction modes as additional coding option. For each coding unit, a flag is signaled which indicates the use of the MIP or conventional modes. There is a total of 30 MIP matrices, divided into 3 distinct sets, which contain all the trained parameters. Depending on the block size, the number of available MIP matrices is 16 for 4x4 blocks, 8 for 8x8 blocks and certain rectangular blocks, and 6 in any other case. Furthermore, an additional flag is signaled which indicates the use of either the original reference samples or the transposed ones, the latter case requiring to retranspose the output accordingly. Together with the mode index, this accounts for 32, 16, and 12 possible MIP modes, thus each matrix characterizing 2 prediction modes. The prediction signal itself is constructed as follows. From the reference samples left and above, 4 samples in the case of 4x4 blocks and 8 samples in any other case are extracted via averaging. Then, a simple shift transform is applied to the reduced input. Given the mode index, a matrix vector multiplication is carried out, followed by the addition of an input-dependent offset. The output vector forms the prediction signal on a regular grid of sample positions. The remaining positions of the original block are filled via a single-step linear interpolation along each axis, using the original reference samples at the boundary. The input and output dimension reductions are designed such that at most 4 multiplications are carried out for each sample to predict. Additionally, the design accounts for about 4 kilobytes of total memory, half of what has been initially desired. At this point, you may ask, why do we need the shift transform and the offset addition? The point is that the corner sample boundary sub L0 is typically close to the mean value of the reduced boundary, and thus also close to the mean of the prediction signal. Therefore, by first subtracting it from the input, thereby replacing the first entry by the bit depth-based mean value, and then adding it back after the matrix vector multiplication, the input vector's magnitude decreases on average. Note that our prediction matrices A originally consist of floating point entries. However, the approximation error due to using the quantized matrices A hat decreases when the inputs become smaller on average. So far, it may not be clear why MIP in its final design is not generally applicable to the chroma component. Thus, let me elaborate on this. First, the chroma blocks in VVC have a limited list of possible intra-prediction modes. Specifically, for the intra-direct mode, the intra mode of the co-located Luma block is used. Now, when chroma subsampling like in 420 format or dual tree partitioning is used, the block size of the chroma and co-located Luma blocks usually differ as shown in the figure below. You may take a look. If you remember, the applicable MIP modes depend on the block size. Thus, when the chroma and co-located Luma block have different set indices, the applicable modes of the chroma block are entirely distinct from the applicable ones of the Luma block. In other words, the application of the direct mode simply was not feasible here. Until VTM 8.0, the planar mode was selected in these cases. The figure below shows an example of a chroma block and its co-located Luma block. Due to the different block sizes of these blocks, the sets of available MIP matrices are distinct from one another. For the co-located Luma block, one of the MIP modes from the corresponding set is applied. Now, applying the intradirect mode for the chroma block, depicted as red arrow, refers to using the same MIP mode as this co-located Luma block. Thus, the direct mode would refer to the wrong prediction mode, because the set of available MIP matrices for the chroma block's size is entirely different. Only after MIP was adopted, we realized that conversely, the block sizes of the chroma and co-located Luma block agree for 444 chroma format and single-tree partitioning. Thus, we adapted the syntax elements and allowed MIP for chroma blocks in these cases. The impact of this modification is quite substantial though. So let's skip into the results section. When the dual tree partitioning is turned off, the bitrate savings for natural content sequences in 444 format using all intra configuration are around 0.25% for YUV content and 0.6 to 1.8% in the components of the RGB content. Notably, in both reference and test, MIP is enabled, which means that the gain solely stems from the extension to chroma blocks. But why is the gain for RGB so much larger than for YUV? Typically, the correlation between the color components in RGB is much larger for RGB content than for YUV1. Hence, the adaptive color space transform tool transforms the residual into an intermediate color space prior to the transform coding stage. The ACT performs a decorrelation of the prediction residual, and thus it works well with RGB content. Now, the presented extension of MIP to chroma blocks ensures that the same prediction mode is used in all color components. Before the extension, MIP and ACT did not harmonize well, and in fact, it was initially proposed to entirely disable MIP when ACT is used. Instead, our solution allows MIP for chroma blocks and provides substantial coding gain. Using the same settings as before, the bitrate savings for RGB screen content averages around 0.4% in the individual color components. Specifically, the gain for TGM sequences is quite low though, which is mainly due to our training database, which consists of mostly natural content high-resolution video sequences. Finally, we want to present performance evaluations of the MIP tool itself after the chroma extension. Therefore, we additionally disable MIP in the reference and measure the bitrate savings without and with the presented extension. The red row highlights how the MIP tool barely has a positive impact on the coding gain for natural RGB content. On the other hand, the green row proves that MIP is capable of producing notable bitrate savings when applied suitably. So what are our conclusions from this? In summary, we have shown how the matrix-based intra-prediction tool can be extended to chroma blocks for 444 chroma formats and single-tree partitioning. We further report substantial bitrate savings for natural content in both RGB and YUV format in the all-intra configuration. Especially for RGB, the described extension also provides a harmonization with the adaptive color space transform tool. More generally speaking, we have also proven that MIP works well when PVC is potentially used for still image compression. The relatively moderate coding gain for screen content is most certainly due to the composition of our training database. Nonetheless, we have shown that MIP in general works well for 444 chroma formats and can be applied to the chroma component. This concludes our presentation. The final slide contains our references and our contact details. So I want to thank you a lot for your attendance and goodbye.